we can get started. Well, it's a pleasure today to have Brian visit us and give us a seminar. Brian, of course, maybe for the students that don't know, Brian graduated from Minnesota, so you can see what happens after you graduate. He graduated. Oh, actually. Yes, so Brian graduated in 2008, and then after that he did postdocs at Perimeter, Chicago, and CERN. And then in 2015 he got a faculty job at Pittsburgh, and that's where he's been since. And today he's going to tell us all about thermal misalignment with scalar dark.
All right, well, yeah, thanks very much, Tony. And thanks to the organizers, I guess, for the invitation. I'll also just say that I owe a great deal of all of my success to a number of people in this room. So I'll just acknowledge that to begin with. It's really a pleasure to be back. So I'm going to tell you about some work I've been doing with my postdoc at Pittsburgh. Akshay Galsasi is really excellent. The title of the work is Thermal Misalignment of Scalar Dark Matter. And essentially what it is, it's a new dynamical mechanism to generate misalignment production of dark matter through a coupling of the ultralight scalar dark matter to particles in the thermal bath in the early universe. So that's what it is, and then I'll spend the rest of the talk telling you in more detail. Okay, so the motivation for this obviously is dark matter. So I don't have to say too much more about why we're interested in discerning the nature of dark matter. There's lots of evidence across a range of scales. In particular, if we think about the theoretical landscape of dark matter, it's actually quite vast. So I've taken this slide from a lecture of Tong-Yan Lin. So it shows basically that dark matter could reside anywhere in the range from 10 to the minus 22 electron volts. This is just so that its de Broglie wavelength fits within a dwarf galaxy, all the way up to things like order solar mass, possibly composite objects like primordial black holes, and then anywhere in between. There's all kinds of potential theoretical candidates that could explain dark matter in this vast landscape. So on the one hand, that's a bit of a problem. We want to try to explore as many of the possibilities as we can experimentally and observationally. And on the other hand, you could ask, like, well, what are some other hints that we could point to try to motivate, maybe narrow down the scope. So what I'm going to focus on today is this region, very light, so-called ultralight dark matter. In this regime, if dark matter is to be make up all of the dark matter, it should be a bosonic field.
Using cryptocurrency.
And so I'll talk about a specific class of models in this
one rich asshole
kind of this low mass part of the landscape.
So that's a lower bound, that 10 to the minus 22. You can't go lower than that.
You can't go lower than that. Yeah, because basically, in fact, there's even, I'll show some bounds later, but you would start to affect structure on small scales. And so
you can go lower, but you cannot have all dark matter. You can have the subcomponent.
yeah, you could have a subcomponent, and
But is
wouldn't-
dark matter ultralight? Dark matter, is it in thermal equilibrium? With
it's not. It's non-thermally produced.
Okay.
Yeah.
That's what I thought.
Yep. So yeah. So even though my title has thermal in it, it's still a non-thermal production mechanism. So we'll have to clarify when it comes to that. Yeah. Okay. So that's the motivation. So this is the plan for the talk. So again, ultralight scalar bosons, they constitute a popular, well-motivated class of dark matter candidates. The canonical example in this is of course the QCD axion. The scenario I'm having in mind is actually not necessarily a QCD axion. We'll see that the interactions that I introduce actually are not the ones you would expect from a typical QCD axion model. The canonical production mechanism, a fairly generic production mechanism, is the so-called misalignment mechanism. I'm going to spend a few slides reviewing what that is in a second. Some questions that come up with this mechanism is the sensitivity to the initial conditions. So the relic density is controlled by the so-called initial misalignment angle. There's definitely some subtlety with this question that we can discuss in more detail. Another question maybe is like how to connect this relic density with short distance particle physics parameters because of this sensitivity to initial conditions. So what I'll tell you about is a new dynamical mechanism, which we call thermal misalignment. The mechanism in a nutshell, it relies on a coupling of the scalar to particles in the thermal bath near the universe that will generate a finite temperature potential that will modify the dynamics of this scalar field and generate this misalignment. And this is a very simple, you'll see it's a very simple mechanism. It can be applied to a variety of different models. And so I'll just talk about one example model where it's phenomenologically viable in a case when dark matter couples to the muon. And we'll outline some of the phenomenology in that case.
So is it, I mean, like, how new is this stuff, right? So in inflation setting, this was played with a lot, right? The so-called thermal inflation, where you have some initial condition for an input on set by thermal conditions. And when it cools off, right, it starts rolling. I think it's called thermal inflation. Right?
Well, that's the old, this way.
Yeah, but I guess the new bet that it applies to dark matter, right?
So you mean the initial field value of the inflaton is set by thermal effects?
Refer to anything like Higgs is initially.
But I think in that case though, for inflation, I mean, you don't necessarily need to set any initial condition, right?
No,
It just has to be long enough period of inflation. That's all.
it used to be, I mean, but that was before that idea was a.
You could have any number of E-folds
Initially,
of inflation.
if you really go back, it was the SU5 symmetry breaking. So the idea was that symmetry restoration for thermal effects that put the Higgs adjoint at the origin, and then you would inflate, and then you have the SU5 gut phase transition. Okay, that didn't work for
Yeah.
a whole bunch of other reasons. And then people moved on, but in the meantime, there was a period where they were still using finite temperature potential to set the initial conditions. And then you have inflation with that starting point from the minimum of the potential. But
Yeah.
then it was recognized that wasn't even necessary because actually when chaotic inflation,
Right.
chaotic inflation assumes, you just, doesn't matter where the field value is, those regions where the field value is in a place where the potential is flat enough, those will inflate and you don't care about the rest of them.
Mhm.
But so it was abandoned, in 1983, that essentially.
Yeah.
83, 84, all those finite temperature corrections.
But Maxime, I would to your question there, I wouldn't necessarily say that, obviously people have explored the impact of finite temperature potential on scalar fields for a long time, but I couldn't find anything in the literature that really does this.
Well,
but yeah.
The new bit then it's application to this ultralight
Dark matter. Yeah. Yep.
Yep.
And as we're going through it, if you see some similarities with other things, even inflation or whatever, I'd be happy to learn more about that to see, because I feel like there's also like quite a few new directions one can pursue, maybe in other contexts, not just dark matter. So I would be happy to learn more. Okay, so I'm going to spend a few slides just reviewing the classic misalignment mechanism, which I guess, as far as I know, goes back to these groups in early 80s in the context of QCD axion dark matter. So let's consider dynamics of a massive scalar field, phi, in the early universe. And we're going to start from some initial field value, phi initial, shown here. And we'll just consider a quadratic potential. And so in the expanding universe, the scalar field follows this equation of motion. Okay, so it's just the equation of motion in the FRW background. You have the Hubble parameter here. You have the mass term here. And let's see what happens with this system. Okay, so at very early times, at very high temperatures, the scalar field will be held up at its initial field value by Hubble friction. Okay, and it will remain essentially constant. Okay, so at its initial value for some time. A little bit later, as the universe cools, the Hubble parameter will drop below the scalar mass. Okay, and that will signal an onset of scalar oscillations. So the scalar field will start to roll down its potential, and then as we go forward, it'll start to oscillate about its minimum. Okay, and so the field starts to drop at this time t oscillation when the Hubble parameter is close to the mass of the scalar field, and then you have oscillations. And so if you study this system, what you find is that the energy density stored in this oscillating scalar field, it redshifts like matter if you average over several oscillations. Okay, so that means that the scalar field energy density scales like inverse scale factor cubed or like temperature cubed. Okay, so it behaves like matter. And so this scalar field can provide a nice cold dark matter candidate. Okay, so it's just very generic scalar field oscillating about the bottom of its potential in a quadratic potential. And so you can calculate then the Relic density that's stored in this scalar field today. And so that's given by this formula. So I take basically the value of the energy density at the time of oscillations. I account for the redshifting from that time on to today. Okay, so there's a volume dilution essentially. I divide by the critical density, and then I can find this parametric estimate. And the key thing I want to point out is that it depends on this initial field value, phi initial. Okay, so if I vary this phi initial, I'll get a different dark matter energy density. And so it's essentially sensitive to this initial field value. And again, this statement that it's sensitive to initial conditions, really you have to then think about what that means when you attach on inflation. And so then, yeah.
I ask a stupid question. If there is a friction term and it is proportional to the Hubble, the energy is dissipated. It's not conserved in the scalar field, right? The energy conservation in the scalar field does not hold, so it is dissipated outside.
It's diluted, yeah, as the
Where
universe
it
expands.
goes.
Well, the universe is expanding.
Yes.
So the energy density per unit volume is decreasing with the expansion. So it's just you have a box, you're making the box bigger, and so you're diluting the
So
energy
if you
density.
put spectator baryons, right, which is heavy particles, right, and you ask the question, how's this thing redshifts relative to baryons? They both redshift at the same time, so the ratio of energies is the same. Right?
Okay.
So it's the same for baryons as well.
So this is very similar to the chaotic inflation starting point, except that it looks like to make it a dark matter candidate, you don't need super Planckian value.
Yeah, that's right.
That's basically.
Yeah, like if you had an inflaton in a m squared phi squared potential, you get exactly the same dynamics.
Yeah.
The axion story is a little more complicated because the potential switches on.
Yeah, that's right.
Is actually switches on
The mass.
gradually,
So
right?
you could think of the mass term as depending on the time or temperature. Yep. So this is just the simplest example in a certain sense. Okay. So let's see where we're at. Okay. So now in a kind of a one-slide description of what I'm talking about, the so-called thermal misalignment mechanism. So this is the kind of cartoon picture through different stages of the universe. So at very high temperatures, above the mass of some fermion, which is in the thermal bath, could also potentially be other particles, a boson or something like this. So at high temperatures, what we'll see is that an effective potential develops, and the minimum of this potential will be at some large field value. And so the scalar field, starting from some generic initial condition, will start to roll towards that minimum. At temperatures of order of the oscillation temperature, again, when the Hubble parameter goes below the effective mass, that thermal piece of the potential will start to diminish, become Boltzmann suppressed, and so the minimum will start to shift back towards the origin, the scalar field will then reverse direction. So this gives you your misalignment, essentially your initial misalignment. And then at late times, it's the same story. You're just oscillating about the minimum. And so the behavior of the scalar field looks something like this. So you start from some relatively small initial field value, and then the field will roll towards large values till the point of oscillations, and then start to oscillate. Okay.
How did you get up the other side in the middle?
Here?
Yeah.
Yeah, well, it depends a little bit on the parameters, but what's happening is just that very quickly at some point, the minimum moves towards the origin, essentially like
Oh, your
instantaneously.
minimum is changing.
Yeah, the minimum will change because the thermal piece will become suppressed, Boltzmann suppressed. Yeah.
So there's a sense of tuning here. Did you estimate the amount of tuning you require to achieve?
What do you mean by tuning?
Right, when you have to like let it roll towards the direction toward large field values.
Yeah.
With a particular typical size of field dispersion, right? Then they have.
Well, yeah, the way I would phrase it is that there are some parameters where you're going to get too large of an oscillation amplitude. There are some parameters where you get too small, and so there's some sweet spot, just like
Sure.
freeze out, right? Like if you have freeze out and you just think of generic couplings, there's some special values of couplings which give you the sort of order picobarn annihilation cross section. Would you call that tuning? It's just some slice in the parameter space.
So sure. I think the tunings are everywhere. I just want to understand, have you ever estimated parametrically this depend on?
Well, yeah, I'll show you a parametric estimate of the relic density, of course, so how it depends on the model parameters. But I wouldn't call it tuning in the sense of like, there's a different type of tuning, which I will talk about, like a sort of naturalness tuning. But this is just, for some parts of the parameter space, you get the right relic density. For some parts you don't, just like thermal freeze out.
I'm still a little bit puzzled. So there's no scales here in some sense.
Yeah,
Very schematic.
I'll get.
Well, wait, I mean, what?
Yeah, this is just very schematic right now.
Potential itself, we're looking at the little balls going down, but the potential itself is moving to the left at the same time as the oscillation,
Well,
at the same time as the field change.
the potential is changing while the field is moving as well. That's true.
Right, so and in this, if I take Keith's suggestion to understand where a zero is, it's moving
Yeah.
to the left.
No,
The
the
minimum,
minimum is moving from from right to left towards the origin. I'll show like a lot more cartoons and some equations
I mean,
soon.
presumably this is from some finite temperature
Yeah.
correction to the potential.
Yes.
right,
Which, okay,
which is due to psi.
Which is due to the effective mass of m psi, the free energy density of the psi particles.
well, but through their coupling to other things.
Yeah,
To the radiation band. right?
that's true. That's true.
Right, because that's where you're getting all the.
Yep.
So those typically, you would write down something, psi, psi is, what is psi?
Maybe if you give me a few slides, I'll explain in more detail. This is just
Well-
like one,
Okay, because normally they would go, the potential then would go with something like t squared phi squared.
I'll show you, I'll explain why that is.
But
I'll-
only for certain values of the field value. That doesn't go up forever like that.
Maybe let me describe it in
That's a-
some more
that's a-
quantitative detail. And
An high temperature approximation
It's a high temperature and field value.
and field value approximation.
yeah, let me go into more details and then come back to it.
Minus phi over t.
Right.
Okay, so so maybe I can go through this quickly, but let me just also, before I get to the details, highlight a few key differences between this classic mechanism and this mechanism, okay, the thermal misalignment. So again, just to emphasize that, in the classic misalignment mechanism, phi oscillation amplitude is just dictated by the initial conditions. In our case, the field is dynamically driven to some large field value, and then it starts to oscillate. And what we'll actually see is that this oscillation amplitude is an attractor. So in other words, it's insensitive to the initial conditions. Okay, so I can start any value of the initial condition will be driven towards this eventual oscillation amplitude. Okay, so that implies then in turn, and that's the contrast with the classic case, right? So if you just change the initial amplitude in the classic misalignment mechanism, you just decrease the eventual oscillation amplitude.
Another difference is that your field, this is not a compact direction. Right? You assuming
It's not a compact direction. No.
Yeah.
It's just a real scalar
Yeah,
field.
you're
Yep.
assuming that you can go out as.
Yep.
soon as you want.
Yeah, that's right.
Okay, so just to clarify, who's misaligned from where?
The scalar field is misaligned from a small initial value to a large value.
So the misalignment is that one should think of it as normally having a small value, but actually it has a,
So the normal case is you start from some large value, let's say,
Right.
and then it rolls down the potential.
and is that misalignment too, or is that?
Yes,
alignment?
that's misalignment. That's what we would call misalignment.
Because it's not at the origin.
Yeah, it's not
at
the origin.
minimum.
Because it's not at the minimum. So
Because the origin
misalignment,
actually doesn't mean anything here yet, because there's no symmetry that is associated with phi, so.
Yeah,
Let's try and get to the equation.
no,
Okay.
I was just wondering what was misalignment?
yeah, that's what it means. That's what
To
it
the
means.
origin.
It's not at the origin. It's
Not at the
The
origin.
minimum, the minimum.
The minimum, wherever.
yeah,
yes.
it's not the minimum. That's right.
Yes.
Okay, so then what this will also imply, I just want to make this final point, that the oscillation amplitude and the abundance then will not be sensitive to initial conditions, and it will actually be correlated with the particle physics parameters of the model. Okay, masses and couplings. Okay, so these are, I'm not saying one is better than the other, but they're different in an interesting way. And also because of these new couplings, you'll have some additional signatures associated with this. Okay, so let's get now to some more details. So the basic toy model that we'll look at is a scalar dark matter phi and a Dirac fermion psi. This fermion is going to be in thermal equilibrium with the standard model bath. It could be a standard model fermion, okay? And so this is the Lagrangian. And so there's a mass term for phi, there's a mass term for psi, there's a Yukawa coupling, we call it lambda. And then actually we're going to parameterize lambda in this funny way, just really for convenience. So we just parameterize it in terms of the ratio of the bare mass of the fermion to the Planck mass. And this coupling beta is some dimensionless constant, okay?
You're okay to have the fifth force, right?
We'll get to the fifth force, yeah. There'll be a fifth force constraint for sure. The couplings that we're going to be interested in are sort of within beta of a few orders of magnitude of unity. Okay, so these are actually really weak couplings, if you think of it in terms of lambda. Now, the key thing for us will be now, if you imagine that there's a background value for the scalar field, this fermion develops an effective mass that depends on phi. Okay, it's just it's m psi times this factor 1 minus beta phi over m Planck. Okay, and then so in this phi background, the fermion free energy density will depend on the scalar field background, and that gives rise to the scalar effective potential, or you could say finite temperature effective potential. Okay, so for the effective potential, these are the three contributions. Okay, so there's the bare potential, there is the Coleman-Weinberg potential, you can say the zero temperature effective potential. And then the key piece for us is the finite temperature, one loop finite temperature effective potential. Okay, so this is the standard result for a fermion effective potential for a fermion in the thermal bath. This is the J function here. Okay, it depends on the effective fermion mass divided by the temperature. Okay, and in a little bit we'll see how this looks in different regimes, high temperature, low temperature, and so on.
Sorry, what the G side?
G psi is just the number of degrees of freedom of the fermion, which would be 4 in this case. The number of, let's say, spin degrees of freedom.
Okay, so this one model is number of one.
Yep. Just number of for Dirac fermions 4. So it's just to keep it, no particular reason to keep it like that, but. Okay, so now, so related maybe to the tuning question, which it's a different tuning. So what we're doing now, at the end, we're going to present our results in the plane of the scalar mass, the dark matter mass, and the coupling. And for now, we're neglecting the influence of the Coleman-Weinberg potential, so this one loop piece. And what that means is that if the scalar mass is very light, that means you're tuning the potential, right? So you're saying that the zero temperature effective potential is tuned, right? So there's just the usual hierarchy problem for having a light scalar field. As we'll see in this realistic model, much of the parameter space actually, this piece actually is negligible. So much of the cosmologically motivated parts of parameter space that you actually don't need to include this correction. But just to keep that in your mind, that we're really only going to include this piece and this piece in our analysis. And the philosophy will be, if we have a very light scalar field, it's actually tuned. Okay. Okay, so now let's try to get into some more details about how this potential looks and how the scalar field will evolve. So we study this effective potential. Again, you have the quadratic piece, and then this finite temperature piece. And so we'll start from very low temperatures, okay, and then we'll increase the temperature. We'll heat up the universe. We'll see how the potential changes. So at very low temperatures, this piece is Boltzmann suppressed, so we can just neglect it. Okay, that's the blue line here. It's exponentially suppressed. The full effective potential is just the quadratic piece. Now we heat up the universe a little bit. So we go to temperatures of order m psi. Okay, temperatures of order the fermion mass. You start to see the blue piece turn on a little bit. Okay, but the quadratic piece is still dominating. Now we heat up a little bit more, temperatures of order 3m psi. Now you start to see a competition between the two pieces. Okay, so the finite temperature piece is starting to grow, and you see the development of a minimum at large field values. And you can understand that from looking at the finite temperature potential. If you just expand this piece, you have the contribution of the effective fermion mass. And you can see that if I minimize this, right, I'm going to get a minimum at m Planck over beta. Okay, and so that's what is happening right here. And then I can keep going. Yeah.
M psi there is,
M psi is just a bare fermion mass.
so it's not the part that has.
Right. There's two parts to the fermion mass, the effective fermion mass. There's a bare piece, M psi, and a piece that depends on the Yukawa coupling.
So I'm a little confused why this is giving you a minimum away from the origin.
Yeah, so it's just really this piece. So if you just think of expanding out this term, you're going to get a piece that goes like t squared m psi of phi squared. And m psi of phi has this piece 1 minus beta phi over m Planck squared. If you minimize that, you find that there's a minimum at phi equals m Planck over beta. That's what we're seeing right here. So it's, in a sense, it's different than the case of the standard model fermions because you don't have a bare mass in that case, right? It's just the t squared piece, t squared Higgs piece. This case, we have a bare mass. So there's a competition between those two.
You're saying, so if I got rid of, if I set m psi, well,
If you set 1 to 0,
okay,
then you'll get what you're thinking that you were familiar with. Yeah, you set 1 to 0.
so now you're requiring fermion.
Yep.
So it's not Higgs.
We'll see how it works in the muon. In the case of in the standard model, it's a standard model fermion, but you still do have it. You can still have it. You can have a Higgs mass plus a scalar coupled to a dimension 5 operator, for example. You can have it.
So all
Yeah.
this happens at pretty low temperatures now.
Yep.
What is m actually? What is the, or what is m psi? What m psi do you have in mind?
Well, we'll talk about the case when it's the muon. So 100 MeV.
So the sign of the Yukawa coupling here matters a lot.
It doesn't really matter. It biases the potential one way or the other. But you could start at, it just depends on where you start your phi field. You could start at negative values or positive values. Actually, it doesn't matter as long as the initial amplitude of phi is smaller than the eventual oscillation amplitude. It doesn't matter. Yep. Yeah.
So the fact that the one loop potential makes a qualitative difference, does that mean the perturbation is actually not very good? You need to include 2 loop and 3 loop for the thermal effects to see where the actual thermal minimum is.
What do you mean it's not a good approximation?
So I would expect that if you include a 1 loop finite temperature potential, if that's just a small perturbation to the potential, then we know 2 loop and 3 loop would be more suppressed and unimportant. But here you're saying that if you add the 1 loop thermal potential, the whole picture changes.
Yeah, it's the leading effect.
But
It's the leading effect at high temperatures.
But how do we know that the 2 loop, 3 loop not
Well, it's, I mean, you have, yeah, I mean, I'm working in the one loop approximation. Yeah.
It's actually not loops. It's,
One computations can change this with the potential.
it's not really loops when you're talking about finite temperature.
Beta
Yeah.
was defined to be.
Beta is very small. Yeah.
Lambda, your original lambda was what? Beta?
Yeah, the values of lambda are like, yeah, let's go back.
Definition of lambda is
Because it was arbitrary. You put M Planck in there.
Yeah, this is extremely small Yukawa coupling.
Yeah, but now don't you have to worry about the radiative corrections to that? Are you fine tuning those away? When I generate that one loop coupling like that?
Well, with this model, you won't generate many. I mean, it would be proportional to the lambda coupling itself, right? It's the only interaction. So I don't think lambda is necessarily fine tuned. I mean, also, yeah, it would be multiplicatively renormalized, right? Lambda, so Yukawa coupling. Yeah, I'm working in the one loop approximation. I can't say if two loop effects would really modify this, but it's the leading correction. Yeah. Yeah, go ahead. Go ahead, yeah. Yeah.
So, am I correct? So, I think in order to have this kind of effect, in order to induce some, finite misalignment, then the motion of the minimum should be first, right? Compared to the mass sphere, maybe.
The motion of the minimum should be.
So, if the motion of the minimum from the potential is slow, then I imagine that
Then you just evolve adiabatically. Yeah.
right. So, are there any separation of the time scale between? I don't know what to compare.
That's gonna come right next.
Well,
But
yeah.
I don't know. It's a good question. That's,
Well,
you would think that it just
Yeah,
tracks
what-
the minimum.
yeah. Well, what we'll,
Maybe I should compare.
I'll just solve the equation of motion and we'll see.
Yeah, I
what
mean,
happens.
that was the issue earlier, right? The potential is changing as the thing is.
Yeah, I'm just gonna take the full equation of motion, solve it, and then you'll see what happens, right? But that will take into account any of that effect, right? I mean, so you'll either see it tracks the minimum or it doesn't, but it doesn't in general. Yeah. Okay. I think we got the qualitative picture now of the potential. So let's go back now to the evolution of the field. So the picture now we have in mind, we start off at some random, whoops, oh, what happened here? Oh, that's interesting. Okay, here we go. So we start off at some random initial field value, basically arbitrary initial condition. There's some caveat, but just let's take that as the starting point. Yeah, in the case of the standard model, basically the fermion mass turns on after the electric phase transition, so that will kind of set our initial condition. Okay, and then we let this go. So this is our potential at high temperatures. So starting from this initial field value, the scalar field will start to roll down the potential like this. Yeah. Yeah.
So what you just said, so if we're imagining that, oh, this is not Higgs, this is a bare, so we're starting, if the Higgs has zero expectation.
Yeah, right now we're not worried about the Higgs, we're just taking a bare fermion mass. But if the Higgs has if we're talking about a standard model fermion, we start with effectively you start the initial conditions at the electric scale, at the electric phase transition.
But the field would be at its origin, because then you would have this minimum at zero. You still have the.
Well, not necessarily, not necessarily.
That's what you said before, you would get rid of the one, and then I have phi squared t squared, so my minimum is at the origin.
It doesn't necessarily mean the field is at the origin though. Field could be at any initial value.
Well, but it'll evolve to the origin.
Yeah, so that's a question about the initial conditions, like say after inflation, does it have enough time to evolve to the origin if it has this really shallow quadratic potential? Yeah.
Well, it's not shallow, right? Because it's t squared phi squared, so it's mass. It has a mass of order t.
No, but
No, it has
let's
no.
see, quite a bit after the phase transition. So what you have are the whatever the hard
No, but
masses.
you're going to compare. Sorry, you're going to compare t with H.
It doesn't have a. I mean, it basically doesn't
H
have an
is t
effective
squared over
potential.
M Planck. So long as you're below M Planck, it will go to the minimum and then track. It'll sit at the origin until the electroweak transition, so you know the initial position.
What I would say is that above the electroweak phase transition, the fermion mass is 0.
Okay.
And so there's no finite temperature potential at this level of approximation for the scalar field.
Why not? Why don't you?
Because there's just no mass, there's no fermion mass.
But you have, you don't need a mass for it.
Yeah, it would be a higher order effect.
No, you get T squared, phi squared, what you.
Well, so the potential would look like, so M fermion, let's think of the muon case. So M muon would be, let's say some Yukawa coupling, Y mu times Higgs, plus now some higher dimension operator, call it C phi times Higgs over some lambda. So this is the effective fermion mass. Now at 0 temperature, below the electroweak phase transition, this is V, that matches on to what I have. Above now, this is a Higgs dependent thing, and the Higgs is going to be sitting at the origin at high temperatures. And so this fermion effective mass is vanishing.
Yeah, but that's fine. But
To this
your
approximation.
DT, your thermal potential for phi.
Yeah.
Will still have a T squared, phi squared piece.
I mean, yeah. So there's a T squared
Well, it's-
M mu of phi squared piece like this. Sorry, M mu of phi. There's this, and where this is M mu of phi. So it depends on, so this piece depends on it couples to the Higgs field. And so the Higgs field though is sitting at the origin. And so this is very suppressed at this level of approximation.
Don't see that.
Well, yeah, maybe let's come back to that point. Yeah.
But you had it before where you said if the bare mass is gone,
Yeah.
then you still have what is the. class-
Right. Yeah. But
T squared, phi
you're right. But it depends on the Higgs. In this case, it
Why
depends
does
on the
it
Higgs
depend
field.
on the Higgs?
Oh, because if gauge invariance, right, you have to write down something like phi L H mu right. So you have to write this down. You have to always keep the Higgs in the game to couple phi to the muon
Oh,
because of standard model gauge
Those are the
invariance.
charges.
Yeah. So you have to include that.
Let's still found out interaction without any game, then you can.
Yeah. You're right. So at some level there'll be a finite temperature piece, and if you go to high enough temperatures, it could be important. So what I'm saying is this all at the level of this one loop of approximation where the effective muon mass is like this. So in that case, what we could just say is I reheat the universe to electroweak scale, and then let it go.
That's my temperature.
Yeah, you know. But I think the effective potential is very suppressed because the Higgs is nailed at the origin at high temperatures. Yeah, and this phi has to couple to the Higgs. Yeah. Okay, so let me sketch again. So yeah, maybe I should go through less sketching, but basically I think everybody knows the picture by now after all these discussions. So the scalar field will start to move towards its high temperature minimum. Then the potential will become suppressed at temperatures of order the fermion mass. It will start to move back towards the origin, and then it will oscillate. Okay, that's the picture. So now let's get on with the more quantitative aspects. So what I want to do now is just solve, honest to God, the scalar equation to motion. Okay. There's a few things to do to make this a little bit easier to handle numerically. The fermion mass is kind of the natural pivot point in this game. So when the temperature is above the fermion mass, that's when we're at high temperatures. When it's below, we're at low temperatures. And so I'll just make this change of variables to this Y parameter. So it just parameterizes it's our new proxy for time or temperature. And then I'm going to introduce this parameter kappa, which if for a fixed fermion mass, you can just think of it as a proxy for the dark matter mass. I rewrite the equation of motion in this language here, in these variables. Okay. They'll see this factor gamma come up. This is depending on the effective number of degrees of freedom, but for our purposes, we just take this gamma to be order 1 number. Okay. All right, and so then we just take this and we solve this equation numerically, and then we can determine the evolution of the scalar field. Okay, so here is one example plot where you see that evolution. So again, I'm plotting the scalar field value as a function of y, which is just the temperature. When y equals 1, this is when you transition from high temperature to low temperature. As you go forward in this axis, you're at going to high temperature, you're going back in time. As you go this way, you're going forward in time, going to low temperature, okay? So what we see is that we start from some initial small field value. The field starts to grow, it's rolling towards its potential minimum until it gets up to some value up here. This is the oscillation time, and then it starts to oscillate, okay? So this is what happens for an actual parameter point. Now I want to, yeah.
On the way up there, it's tracking the minimum, is that what's going on?
No, it's not, it's moving towards the minimum. It's not tracking the minimum. Actually, in the parameter space where you actually get the right relic density, you actually never get to the high temperature minimum. You actually never reach it.
So it's proportional to the slope.
Yeah, it's proportional to slope. The slope governs everything for this initial phase. Yeah. Yep. So that's what I'll discuss. Yeah. Okay. So I want to understand this evolution in a little bit more sort of analytic detail. Okay. So the first thing we'll do is just try to understand what the effective potential looks like at very high temperatures and where the minimum is. So at high temperatures, again, we can write the effective potential out. We have a bare mass, and then we have this temperature dependent piece, okay? And we can minimize this, and we can just jump to the results. So there's two regimes basically. So at very high temperatures or very large values of y, the minimum is just at m Planck over beta, and that's because this piece is dominating, right? It's at high temperatures. T is much larger than T is very large, so this piece dominates. And so you can see minimizing this, I'll get phi equals to m Planck over beta. Okay, so at very high temperatures, it looks like this. And then at some point when temperature decreases, then, but we're still at large values of y greater than 1, then you get this behavior. So what it says is that the minima is now moving quickly back towards the origin. Okay.
What is kappa?
Yeah, kappa is essentially it tracks the fermion mass, but it's just this dimensionful parameter. It tracks the dark matter mass. So if I think of fixing m psi, it's just a variable for m phi, a dimensionless variable. Yeah.
What is y effective?
Yeah, sorry, y effective. Where is that?
Oh, there, the second line. Lower temperature, but y effective.
Oh yeah, sorry, I'm sorry. Y effective. Y effective is just it's m psi. It's m psi of phi divided by t. Yeah, don't worry about it. It's just high. Just think of high temperature. It's just high temperature. Yeah. Yeah, I shouldn't have put that there. Sorry. It's lower T, but still the temperature larger than the fermion mass. Yeah, sorry. Yeah. All right. Next, we want to understand this initial phase of the evolution. Okay, so the initial trajectory, what we can basically infer is that it's this slope term, this linear term in the potential, which is dominating the dynamics. And so actually the scalar field will sort of slow roll. Okay, so the acceleration term is small. We get this very simple equation of motion. Okay, so you can solve this. You can give it to your freshman students. And this is the solution. So it just says that phi is increasing with time. Okay. Yeah, terminal velocity. Yeah. So now, if you look at this solution, I want to highlight a couple of things. So since we're starting from some early time, that means we can neglect this piece, right? Ti is much smaller than our eventual oscillation time. Okay, and since we're assuming we start from some small initial field value, we can neglect this piece. And so what this tells you is that the trajectory is not sensitive to the initial conditions, provided you start early enough and from small enough initial field values. Okay, and you'll always match on to this trajectory. So, and you can see that in this plot for several different choices of the initial conditions. You just track this trajectory here, this dashed line. Okay. So now we would like to know when the scalar field starts to oscillate. When is the onset of oscillations? So, so this will happen when the effective temperature dependent mass is equal to the Hubble rate. Okay. So this is the effective temperature effective potential mass. It has the bare mass plus this t squared term. Okay. This is the Hubble parameter. Again, this gamma just is parameterizing our G star. And we set this condition to estimate the oscillation temperature. And we find these two limits, okay? This is for, again, high temperatures. So when the oscillation temperature is greater than the fermion mass, we find these two regimes, okay? So basically for large couplings or for small couplings, you could think of dividing it in that way. Now, there's also a possibility that the oscillations happen at low temperatures after the effective, the temperature dependent piece is turned off. Okay, and in that case, you just neglect this piece, and so it's the bare mass which will enter. And so then that depends on this factor, again, square root of kappa. It's just depending on the scalar mass, okay? So for the regions that give the right relic density, it's really gonna be that the oscillation temperature, or Y oscillation, is square root of kappa, goes like square root of kappa, okay? Or goes like the dark matter mass, okay? And we can divide now up the parameter space into three qualitatively different regions, okay? And then we can study the relic density in each of those regions. These regions are delineated by the condition whether oscillations happen at high temperatures or low temperatures relative to the fermion mass. Okay, so Y oscillation equal to 1, and whether or not the coupling beta is large compared to this dimensionless parameter kappa. Okay, so if we divide up the parameter space, it looks like this. So we have a kappa beta plane. Kappa, again, is parameterizing the dark matter mass. It goes like m phi, square root of m phi. Beta is the Yukawa coupling, the effective Yukawa coupling. And so what we'll see is that in this region, you actually don't get the right relic density. You overproduce dark matter. So I'm basically not going to discuss this region, okay? In these two regions, you can get the right relic density, okay? And so I'll call this one region 1 and this one region 2. And basically they're at small values of beta, but you can have basically any dark matter mass, any scalar dark matter mass. Okay, so now in region 1, let's try to estimate the relic density. Okay, so region 1 is over here. It corresponds to small Yukawa coupling, larger dark matter mass, and oscillations starting at high temperature above the fermion mass. Okay, so that's the region we're in. Okay, so we just take our initial trajectory. Okay, that's just shown here. We've estimated the temperature at which oscillations start. Okay, so we know when oscillations start. That's given by this expression. Just goes like square root of the dark matter mass. We plug this value of Y oscillation in here. That tells us our oscillation amplitude at the onset of oscillations. Okay, and so we have this oscillation amplitude. We can estimate the relic density then at that time. Oops, the energy density at that time. It's 1/2 m phi squared phi oscillation squared. We account for the volume dilution from that point on to today, divide by the critical density, and we get this kind of parametric scaling. Okay, so it goes like beta squared over kappa to the 3/2. Okay.
But why do you say small beta? Because I can take very large in region 1.
In region 1, you mean like up here?
Yeah.
Yeah, that's fine. But I just mean it's smaller than up here. That's all I mean.
Oh, okay.
Yeah, that's all I mean. Yep. Okay, so and so this is the parametric dependence. We can go back to our parameter slice, and then we can make a plot. Okay, so this is what along these lines is where you get the right relic density for different choices of the fermion mass. Okay. Now we can go into this region and look at the same thing. Okay, so in this region, we're now at small beta in the sense I just mentioned, and also small kappa or small dark matter mass. Okay.
What are the values of lambda that correspond?
Well, it would be the fermion mass divided by m Planck times beta. So it's very small, extremely small.
No, but then related to Keith's question, there would be a perturbative limit then, right? I mean, as m psi and beta, you make beta very large and.
No, but these are very small Yukawa couplings.
No, but beta you could make large relative to m psi over m Planck, right? Because
Well, m psi over m Planck though is extremely small. It's like muon mass over Planck mass.
But
It's
that's
tiny.
what I'm saying, you can make beta.
Oh yeah, but I'm never going that high.
But why? That line continues going off.
Yeah,
But then the mass is very big, right?
Yeah.
yeah, the mass will get larger. There also are some constraints out
So
there.
there's never any.
No, there's never, not even close. This
For
is
any parameter
extremely,
space.
yeah,
Yeah, I see.
extremely weakly coupled.
Okay.
Yep. Okay, in this region 2 now, we're at the only difference now is that the oscillations happen below the fermion mass, so at late times. So again, what do? We take our initial trajectory going up the hill. And now what happens is at y equals 1, the fermion free energy density becomes Boltzmann suppressed. Okay, so the effective potential drops out, and then we kind of just plateau. Okay, and so basically you could just plug in roughly y equals 1 here to get the parametric estimate for the oscillation amplitude at the onset of oscillation. So it just goes like beta times m Planck. And then we put everything together again. We have the energy density at the onset of oscillations. We account for the dilution effect, divide by the critical density. And so we get this parametric dependence. It goes like beta squared times square root of kappa. And then we can make this plot. Okay, so then this is how it looks in region 2. We can put these together, extrapolate, and then we can also just check against the numerical solution by just solving the equation numerically all the way throughout. And it agrees quite well. Okay, so that's the basic idea of this thermal misalignment. Okay, so just a coupling of it is very simple, coupling of a scalar to a fermion in thermal equilibrium. The fermion thermal free energy density will generate some dynamics for the scalar field that will roll towards its high temperature minimum, generating misalignment, and then at late times it will just oscillate like dark matter. Okay, so it's very simple.
So the fact that we couple to temperature could be useful if we try getting it from side curves.
Yeah, that's a good question. So we didn't really investigate it. You can get away from those constraints also perhaps like depending on how your inflation sector looks, but you're right. So since you're growing, since the scalar field amplitude is growing dramatically after inflation, that could suppress isocurvature perturbations. Yeah.
Well, it's also just that you've done an attractor, right? So
yeah,
independent of what those fluctuations are, they'll evolve to the same.
Right. Yeah, so I confess we haven't studied this in detail, but I think there is a lot of potential just to completely suppress isocurvature perturbations.
Yeah, so I just want to confirm the picture. And the picture is my initial field dispersion is a sort of random, so long as it's not
Small.
So long as it's small.
So long as it's small.
They will evolve to a same terminal
Yeah.
or a terminal location before I start off.
It'll always come onto this. Whoops. It'll always reach this this trajectory.
Yes.
Okay. That's what it will always do.
Okay.
So you always get the same solution. You'll always get this initial
Okay.
same solution,
I see.
regardless
So
of
you're
initial
saying
solution.
I'm going to reach the same terminal location of my
Yeah.
field.
Yeah. For a given. Yeah. For a
No
given.
matter where I
For a given set of model parameters, you set any initial condition, you'll reach that point.
Yeah, so that's a tuning I want to estimate, but here you seem to be robust against the initial.
Yeah, there's no, yeah, that's one of the main qualitative differences between the usual misalignment mechanism in a sense. Yeah. Okay.
Also,
Yeah. Oh, sorry.
independent question. Here your scalar field is a real degree of freedom, or?
Yeah, it's just a real scalar.
Yeah.
Yep, in this setup. Yep. Okay. Yeah, so now I just want to make a few comments about inflation and these initial conditions. So, so during inflation, the evolution of this dark matter scalar field will involve a competition between classical rolling and quantum fluctuations. Okay, and so given a long enough period of inflation, so say if you have just again a quadratic potential for this scalar field, if you have a number of e-folds, which is something like Hubble squared over m phi squared, what you can see is that the distribution will of scalar field values will approach a Gaussian with a mean close to 0, but a variance that's given by of order 8 Hubble to the 4th over m phi squared. Okay, so this can be seen, for example, in this paper. And what we need is two conditions to be met to basically set the stage for our thermal misalignment. We need that this variance should be small compared to the eventual oscillation amplitude, so that basically we have a typically small initial field value relative to the oscillation amplitude. And we need the reheat temperature to be larger than the oscillation temperature, right? So that it has time to actually reach this trajectory and start to oscillate. So these are the two conditions that we need to satisfy. And you can show that you can always satisfy these conditions for some suitable range of values of the Hubble constant during inflation. It typically requires a low Hubble scale during inflation and a long period of inflation. Okay. It could like below the fermion mass, for example, below the fermion mass. But you can have that. And a long period of inflation. So anywhere from like maybe 1,000 to 10 to the some number of E-folds.
And how do you reheat them?
We're agnostic about how reheating happens.
But your HI is going to control your reheating temperature.
Well, it's possible to reheat. I mean, it's possible to have such low models of inflation, low Hubble values during inflation. Like there's enough energy density to reheat the universe to, temperatures of order weak scale or something, for sure. The details of how you do it, I mean, probably there's many ways. Yeah, it's not your, maybe it's not your favorite inflation model.
So the Hubble is what scale is did you say it was?
It could be, it should be below the fermion mass, basically.
Which is what scale?
100 MeV.
Oh.
Why is that?
Oh, I
Because
see.
otherwise the initial.
Yeah, to satisfy these two conditions, basically. It's pretty low, but it's possible. It's possible.
Well, you're saying it just has to, are you assuming you just have to reheat?
Yeah.
PBN, that's it?
Yeah.
And
The reheat temperature just has to be above the oscillation temperature.
and
So above the fermion mass,
you
but
have-
so it could be anywhere above. Yeah.
you have to say have some creative way of getting there.
The reheat temperature could still be much higher.
Oh, much.
Yeah, the reheat temperature could still be much higher than the fermion mass. It's just that
Yeah,
the
it
Hubble
would-
scale during
I
inflation has to
mean,
be,
typically it would be
Yeah.
the fermion mass times m Planck. Or well,
yeah, square root,
h times m Planck,
Yeah.
square root of h
Yeah.
times m Planck.
which is fine.
Yeah, right.
Okay, so anyway, we haven't studied like inflation models, but these are just sort of, generic statements. So the inflation sector may have to be a little bit, something that you might not usually imagine, but it's not, it's definitely possible. Definitely possible to do that. Yeah.
Well, with that goal of h, then you have the other issues about how you get the density fluctuation.
You mean you get the right scaling amplitude?
Yeah.
Um,
But then, okay, but you're not worrying about it. I mean, that, like, imagine you can mock something up. Because usually that's related also to age.
Yeah, I guess. So this paper studies this for the case of an axion with, over a broad range of FA, and they've studied this issue. They can get the right. I have to admit I haven't fully worked out the details of the inflation sector, but like at least it seems like these two conditions can be met. That's what I'll say at this time. Yeah. Okay. Okay, so now let's see. So how far I'm. Okay, so maybe I can do this probably in 5 or 10. So now let's look at a realistic model where the dark matter scalar is coupled to the muon. Why do we choose the muon? We actually chose the electron first because that's why not. But it turns out that the electron case in the regions where you get the right Relic density, it's basically quite constrained already. So it's almost ruled out. So it's not really phenomenologically viable. So then we looked at the muon. But I don't have any better reason than that. Sorry. Okay, so this is the coupling now that we just replaced psi with the muon. There's this question about what it means the initial conditions. So what we can just have in mind now is that the reheat temperature is relatively close to the weak scale if you want, and that will set the initial conditions. Once the electric phase transition happens, the muon will get a mass, and then you just the scalar field will start evolving. Okay. Coming back to the issue of the fine tuning, so now I do want to actually pay attention to where this one loop effective potential at 0 temperature will play a role. And so we can just do a very naive estimate of that, which is the usual, sort of quadratic divergence calculation. And so this is the condition that will satisfy. Just take the Yukawa coupling squared, cut the loop off at the VEV of the Higgs. Okay, so that's our UV cutoff essentially. And then we just ask that correction is smaller than the actual scalar mass. Okay, and so I'll draw a line in the parameter space where this occurs. Okay.
Oh, I see. It's the Higgs VEV.
Yeah, V is
That's a very small number, right?
the Higgs VEV.
Oh, no, the thing in the middle there.
Yeah, well, we're at very small beta and very small mass. So there's actually a line. Yeah, there's a non-trivial part of the parameter space, which this is important for.
I still don't understand why I think the potential can be ignored above the electric scale, because I feel like so first of all, you can have the two contribution.
Yeah.
Like the H side to side.
Yeah.
I feel like in that case, maybe you have a additional loop separation, but I feel like that contribution is just replacing the B by T.
Yeah.
The temperature. So and high temperature T is that. So
Yeah.
I'm pretty sure whether that is.
I'm also not completely sure. Okay. But all I was just going to say is that if you just restrict to this one loop contribution, then it's suppressed. So you have because basically this coupling has on the Higgs field. The Higgs field is at the origin.
Yes,
But you're right. There's going to be corrections that depend on temperature. So yeah, I expect if you go to high enough temperature, it's going to be relevant. So in that case, just imagine that we reheat to the electric scale. So that's our starting point. But yeah, I think it's interesting question, like what.
Even
What-
the electric scale, I feel like you just replace this one loop potential to the just replace the B to make one loop potential to temperature and put just additional one loop factor, no, or two loop factors.
Well, in this case, it would be probably.
You always will have to have a Higgs field coming with it, I think.
I'm not
So-
really sure whether you need a, because I think in this case, one loop is like, you have fermion, and then you pick up the wave of Higgs, right?
Yeah.
But then I think in the two loop case, you just close this Higgs line.
Mm.
So I don't think
Yeah.
additional equal coupling.
But if you are above the electric phase transition, for example, you're always, if you erase Yukawa coupling, you get zero.
Yeah, I don't know that it hurts you though, because
Okay.
that's
Talking about the
the field at the origin as your initial condition and you want it.
Yeah, it's fine if it's at the origin initially. No problem.
So it actually helps your argument. but-
Yeah. That's a good point. Yeah, I haven't thought about it. Yeah, that's a good point.
Do you show us the?
Yeah. Okay. All right, maybe I'll just, there's a bunch of various constraints. Let me just actually skip through most of this, unless people want to hear about it. But I'll just get to the money plot, and we can discuss further if people are interested. Okay, so I'll just describe the parameter space and say what the constraints are, and then if you want to discuss in more detail, we can. So what we're plotting here now is, again, for the muon phi coupling, this is the scalar mass now, the dark matter mass. This is the coupling beta. Okay. The blue line here is the exact numerical evolution prediction for the Relic density, including the effect of varying G star as a function of temperature. And then we have a variety of different experimental constraints on here. So at very low masses, this is essentially kind of fuzzy dark matter constraints from Lyman alpha forest flux power spectrum. Okay, so that tells you about the matter power spectrum at small scales. And so very light dark matter just depends on its gravitational interaction. Very, very ultralight dark matter will be ruled out because of that. Let's see, so we also have, over here, we have constraints from black hole superradiance. Okay, so if you have an ultralight boson, it can form essentially atomic states with spinning black holes and extract angular momentum from those. The fact that we observe such spinning black hole systems allows us to place constraints in this window here. And
So everything above this EP line is excluded.
yes, everything above the EP line is excluded. Yeah, I'll get to the EP.
That's principles.
Oh, yes.
Give me a second. Yeah. Okay, so then before that one, I want to talk about the one probe that actually relies on the coupling to muons. are these purplish regions. So these come from neutron star binary systems, which are neutron stars are muon-rich environment. If you have a light force carrier that couples to muons, you can, for example, dissipate power by radiating the force carrier. You can also have a long-range force, which affects the in-spiral phase. And so there are these various purple lines, which could either already constrain, or in the future could, with certain observations, could also cover some of this parameter space. We have the equivalence principle constraints, which come here. So you just have a light force carrier coupled to muons. It will then, at one loop, it will couple to photons, for example. And so that will cause a new force, long-range force. And so there are constraints from equivalence principle tests. These are the orange line. Everything above the orange line is ruled out. There are constraints on time-varying fine structure constant from atomic clocks, shown here. And then this is a projection from future atom interferometry experiments, also trying to measure essentially time variation of, say, fine structure constant.
So this constraint is because you have saturated the dark matter, right? This is
Yeah, that's right. Everywhere. So for putting the constraints, when it depends on the dark matter density, we assume throughout that by whatever means, the dark matter makes up all of the relic density.
Because typically the fifth force is more sensitive.
Yes.
Unless you saturate it.
Yeah. So if you want to take the other point of view, if you want to take the point of view of like, this is how you produce the dark matter no matter what, everything above the blue line is ruled out because you overproduce.
Yeah.
And then you would have to rescale the constraints below the line, that the ones that depend on the local dark matter density.
What's the difference between the dashed blue line and the solid?
The dashed blue line is this approximate formula that we had earlier.
Oh.
Whereas in this case, we're numerically evolving it and including also the differences in the relativistic degrees of freedom as a function of time, which changes things slightly.
So below the blue line,
Yeah.
some of these constraints should actually get.
If you don't assume that it's, if you just assume it's produced in proportion to whatever this mechanism predicts, that's true. You would have a different, yeah. So this is one way to make the plot, just to kind of get a sense of where these different constraints are lying. And then there's the naturalness line. So this is the one for the mass term essentially. So all of this region over here is, you would say, is like technically natural according to that criterion. Whereas this region over here is, you would say that the zero temperature potential is tuned. Okay, so that's the summary on this particular model. So there's a range of still parameter space that's still allowed, and some interesting experiments that could possibly probe them, in the coming years. Okay, so that's essentially what I wanted to tell you about. We've talked about a new mechanism, which we call thermal misalignment. It's a way to dynamically generate misalignment from a coupling of scalar dark matter to a fermion in the thermal bath. It's insensitive to the initial conditions of the scalar field, provided that it's initially small enough. The relic density is controlled by the particle physics couplings and masses. We've shown that in a particular example where dark matter couples to muon, it's a phenomenologically viable scenario. There's some interesting possibilities for probing it in the coming years. And I think that really there's quite a range of different scenarios you could actually apply this mechanism to. So we're investigating some of them at the moment, couplings to different fields of different spins, the Higgs portal as a UV completion, and so on. So thanks very much.
So I have two questions. The first one is that in some cases, even when the temperature is lower than the fermion mass, you still have some thermal correction to the potential. For example, the thermal lock potential. Does that occur in your case?
You mean like, for example, from the couplings to photons or?
No,
or like
just from the coupling between, yeah, the coupling between the fermions and photons.
Yeah, we did look into that. What essentially we found is that, right, so basically the way you could view that correction is take the two loop QED free energy density, which goes like E squared, electric charge squared. And now if you have the muon, which its mass depends on the scalar field, then that's going to give a correction to the running coupling E, electric charge. And so from that, you can basically extract the contribution of, say, the photon correction to the effective potential. And you get this log, basically you get log of 1 minus beta phi over m Planck, something like this. It goes like t to the fourth alpha squared.
I see.
Okay, and so you can check that in all of this parameter space, that effect is subdominant to the bare muon coupling.
I see. But what about the generic case where you should?
Generic case, I don't know, but yeah, that's a good question. So that's something interesting to investigate. Just suppose you just said not even coupling to muons. Suppose you just said, let me write down a scalar coupling to 2 photons. What does that do for dark matter? So that would be an interesting question. We didn't investigate it yet. Could you get the right relic density from that? That would be interesting to look into. Yeah, but at least in this model, the radiatively induced effect from the muon coupling is subdominant in this parameter space.
And my other question is that in the large beta and small kappa limit, and you have some issue with the tuning. Is that labeled by the coordinate?
Yeah, that's right. Yeah, so in this region, the one loop, the Coleman-Weinberg potential is large. And so what it means in a sense, like to interpret it in our scenario, it means we're essentially tuning the potential to have a quadratic form. Yeah.
And are we able to draw those lines in the earlier generic plot?
Well, yeah, maybe it's somewhat easier in this case because there that you could imagine completing this at the weak scale. Like you could imagine, for example, at the weak scale, maybe there's something that comes in and tames all of the sensitivity of the scalar mass to further UV degrees of freedom, maybe like supersymmetry or something. So maybe it makes sense to cut it off in that case. In the other case where you just have a generic fermion and scalar, maybe the question is like, where do you cut it off? So you could cut it off at the weak scale and draw a line if you want, but you could also imagine maybe actually that's cut off at some lower scale. You could have maybe supersymmetry in a dark sector at some lower scale or something. So yeah, it depends on the assumption.
Thanks.
Why does the phi only couple to the muon? So this is how the UV completion. That's what you meant.
Yeah.
Dimension 5.
Yeah.
Yeah, but you can couple to any flavor.
You could, yeah.
No, I can tell you that you couple to a heavy quark or something like that, right?
Yeah.
The equivalence principle line will
Oh,
jump
okay.
down by 2-3 orders of magnitude, just because you are not paying price for alpha electromagnetic when you calculate because
you have a coupling of gluons.
Photons are sourced by the
You have coupling of gluons at one loop.
right. It couples the gluons, it couples to the whole mass right away. So this line will be far more powerful. So
But the relic density line may also move, so we don't know.
yeah.
Yeah.
So the way that's why here beta is only 10%. The coupling is only 10% of 1 over m. Or if we go to the quarks.
Yeah.
Okay,
But Tony, yeah,
I'm not just saying that those models would be ruled out, but I'm just saying.
you're asking more from like what's the motivation for this coupling? Where's it
I
coming?
mean,
Yeah,
it's
I don't know.
from an effective build
Yeah, I don't know.
point of view, phi should couple
Yeah.
to any
Yeah.
fermion, right?
Yeah. So this is a toy. It's again like a toy. You could say it's a toy model if you want.
So,
there
so that
is
means that
one-
there's some kind of tuning that you have to arrange in the UV theory that phi only couples to the.
But it's
muon.
technically
It's not
natural.
tuning.
It's technically natural though. Like
Yeah,
once
it's
if I just write this down, I'm not going to induce large couplings to top quark and it's going to change the story. It's not.
The thing that Brian just said, you can actually consider a Higgs portal, then it's a unique operator.
Yeah.
Right down a trilinear, and it's the.
Yeah, so we're looking into that case.
Lowest dimensional operator, there is no issues of incompletion, nothing, right? So that's.
Yeah, but I don't have I don't have a great motivation for the muon. It's just a simple example, which is viable. But really, I think the interesting thing about, I mean, depends on your point of view. I mean, it is interesting that in this model, you get a lot of interesting signatures that are connected with the relic density. So that's, I think, a very generic consequence of the setup. But I think it's really the mechanism which can be applied in, I think, in a variety of different contexts.
And the
so-
scale, I mean, that you wanted 100 MeV and also very light and phi. Did it have to be down at in that range, or could everything have been shifted up somewhere else?
Yeah, I think you can shift it up. So you could have, let's see. Yeah, so this is really, in some sense, this is like the more model independent parameter space, like where you've kind of extracted out the fermion mass. And so kappa is some dimensionless combination. And so you could, we haven't, looked in too much detail, but I think you could move the fermion. Like if you just had add a BSM fermion, which is coupled to the thermal bath, that's say heavy, you could then have a completely different
I
range.
mean, the one that comes to my mind is a right-handed neutrino.
Yeah, that's a really good example. So that's one we should look at.
So
it's
then
very
you don't
well
need the
motivated.
Higgs. Then the Higgs wouldn't be entering in because you would be doing
Yeah,
n or n bar
like phi n squared or something. Yeah,
Right, phi
yeah,
n
yeah,
squared.
that's a really good
It
example.
just simplifies it because the Higgs.
Yeah.
You don't need the dimension phi.
Yeah.
You don't need.
Yep. That's a really that's a well motivated case to study. Yeah, we haven't
Now
studied.
you're coupling it with singlet. Standard model singlet.
Yeah, so how you keep it in thermal equilibrium maybe is a question,
No,
but
no,
maybe the
N-
Yukawa can
N
do
is
it.
coupled, N is
Yeah.
still coupled to the Higgs and,
Yeah.
and left hand and
Right.
the left hand is
Yeah.
sector. So
So as long as the Yukawa coupling is large enough, it's fine. It would work.
right, so
Yeah.
you
Yeah.
think of third generation
Right.
right-handed neutrino, you have an HLN coupling.
Yeah, I think that's an interesting case to study. That's a very well motivated case. Yep.
But your scales will be very different.
It could be, yeah. It'll
You
depend on
don't know
the,
what the mass of the right-handed neutrino is, but that
it could be anything.
almost anything.
Yeah,
So,
yeah. It could be very light. It could be very heavy.
you can tie it to leptogenesis.
Yeah. So I feel like there is a lot of things to do thinking about it. This, I don't know, like again, so yeah, if any of you have seen things that are similar to this that I'm not aware of, we did try to dig through the literature and we found some things that are maybe analogous, but not quite what we're doing. So I'd be happy to, if you know of any research that's kind of along these lines, I'd like to, learn about it. And
The h to the fourth over n squared, there's no.
oh yeah, okay, yeah.
That's not 19, it's not 2018. Right?
Yeah, this reflects my ignorance of the inflation literature. Yeah, sorry about that.
Okay, well, with that, let's thank Brian again.